Hi Math 34 students. This is Module 8. Make sure that you first read your vocabulary and also possibly work through the OLI software. This is inference for one proportion, and this is tied closely to Module 8 in the OLI software. So example 1 is about calculating the margin of error. A recent survey of LMC student majors found that psychology was the most popular major, and the sample consisted of 326 students, and the sample proportion of students majoring in psychology was p hat equals 0.17. So we call this mark on top of the p a hat, or you could call it a caret. And remember, the sample proportion is the point estimate for the population proportion, but remember, it's almost always wrong. So because it's almost always wrong, we're going to look at interval estimates to see just how wrong or how close to being right it is. So our first question A asks, is this categorical or quantitative data, and explain. So they're measuring student majors, so those definitely aren't numerical, so this is categorical data. So let's explain here. So we can say real simply this is categorical data because the LMC student majors are categories. Now it's asking us to use the sample proportion to calculate the estimated standard deviation. So this formula is on the front of your activity packet, or on page 143, the front of Module 8 in the activity packet. So we're going to calculate the estimated standard deviation. And when you type it in your calculator, you're going to use the square root key, and then in parentheses, or if you're on the 84 plus, you'll actually have the square root sign. We're going to put 0.17, that's our p hat value, times 1 minus 0.17, all divided by the size of our sample, which is 326. And then remember to close off the parentheses if you're on the 83 version, where you've got the square root inside the parentheses. So when we total this up, rounding to 4 decimal places, we'll get 0.0208. So this isn't the actual standard deviation because our proportion is, remember, just an estimate for the actual population proportion. In most statistics, we are not able to survey the whole population. So we take a sample, and then from that we try to extrapolate and make predictions about the whole population. Okay, so from our 68, 95, 99.7% rule, we know that for these confidence levels, 68 ties with 1 standard deviation for the margin of error, so above or below by 1 standard deviation from the mean. 95% corresponds with 2 standard deviations, and 99.7% corresponds with 3 standard deviations. So we're going to use this data from the 68, 95, 99.7% rule to answer questions C, D, and F on the next page. So our first calculation is a margin of error and confidence interval range for 68% confidence, and then we're going to interpret what that means with a sentence. So we know 68% confidence corresponds with a z-score of 1. And we can go ahead and calculate this out. We can say 0.17 plus, now we just need to add 1 standard deviation, 0.0208, and that equals 0.1908. So that's what we would call our upper bound. So I'm going to put an upper bound in front of this. Now we can go ahead and calculate our lower bound by doing a similar calculation with subtraction. And so in our lower bound, we're saying 0.17 subtract 0.0208, and we get 0.1492. So we can interpret this to say that we are 68% confident that the population mean is in the interval 0.1492, so I'm typing the lower bound first, up to 0.1908. So now let's go look at a confidence interval for the 95% confidence interval. Oh, and another note is that these values that we calculated using 1 times the standard deviation, that is the margin of error. So we could add a note, 0.0208 is the margin of error for 1 standard deviation. Okay, let's go ahead and look at the 95% confidence interval. Okay, so 95% confidence corresponds with a z-score of 2. So our upper bound here is going to be 0.17 plus 2 times 0.0208. And when we total that up, we get 0.2116. So that's our upper bound. Our lower bound is going to be the same calculation except with subtraction, because we're going below to the other side of the mean. Okay, so now we can summarize that we are 95% confident that the population mean is in the interval 0.1284 all the way up to 0.2116. And then the margin of error is 2 times 0.0208, which would be 0.0416. So this is the margin of error for one standard, or for not for 1 standard deviation, I'm sorry, for 2 standard deviations. And now we can go ahead and calculate the margin of error in the confidence interval for a 99.7% confidence interval. So 99.7% confidence corresponds with a z-score of 3. So our upper bound is going to be 0.17 plus 3 times the 0.0208. And our lower bound is going to be 0.17 subtract 3 times 0.0208. And so now we can say that we are 99.7% confident that the population mean is in the interval, oh, I forgot to put the totals. So if you total this up, our upper bound is 0.2324, and our lower bound is 0.1076. So we are 99.7% confident that the population mean is in the interval 0.1076 and the upper bound 0.2324. And then if we were going to calculate our margin of error, that would be 3 times 0.0208, and that would be 0.0624. And so that's the margin of error for 3 standard deviations. So remember, we're predicting where we are confident that the population mean will be because we don't actually know the population mean. When we make these calculations, we can usually only get data from a sample of the whole population. And from that data, we have to make extrapolations and predictions about the whole population. So notice, as we get more confident, the interval has to expand. So if we're 68% confident, we have a smaller interval because that leaves more room for doubt than if we have a 95% confidence. Notice the interval gets bigger. And to be 99% confident, we have to have a pretty big interval. So now we're going to talk some more about interpreting the z-score values. Remember, the z-score measures how many standard deviations a statistic is away from the proportion. And the proportion is the center of the graph. Remember, it's a proportion because we're looking at categorical data, right? So our proportion lies where the mean would lie in the center of our normal distribution. And so that 68, 95, 99.7% rule that we use is approximations of z-scores. So mathematicians actually calculate accurate z-scores by measuring the area under our normal distribution curve. And the ways to do that, there's two ways. One way is calculus, and the second way is to use a computer to numerically approximate. So what the computer does is it chops the graph into super small pieces and then estimates the area of each piece. And usually it chops it up into little square pieces, right? And then it counts up the squares. So even after calculus, usually we always use the computer because it's much faster than calculating it by hand. So because we can calculate by measuring this area, we can find the z-score for any possible percent confidence interval. So using what we know about the 68, 95, 99.7% rule, what would you guess the z-score is for 90% confidence? Well, we know that 90% is between 68% and 95%. So then we must expect that the 90% z-score is between 1 and 2. This makes sense because we know that 90% will fall between 1 and 2 standard deviations. On the normal distribution curve. Okay, so it makes sense to everybody? 90% gonna fall between 68 and 95%. Then question B asks, well, how many standard deviations would you expect for a 99% confidence interval? Well, okay, we know 99% is between 95% and 99.7%. So then we expect that the 99% z-score is between 2 and 3. And this makes sense because we know that 99%, if you're imagining it on your normal distribution curve, it will fall between 2 and 3 standard deviations on the normal distribution graph. So remember back in, I think it was module 3 or 4, when I made you estimate, it was module 2, maybe module 2D, I made you estimate where the values would be. Now we're going to be able to use the computer to find the actual z-score, and so we can calculate exactly where values will fall. So here's a sketch of the 90% confidence interval, and we want to figure out what's the z-scale, z-score. So if you look inside, you can see here's 90% inside, and then the z cutoff, they rounded it a little bit here. They put 1.65. So we can see below it's actually 1.645 if we go to 3 decimal places. So depending on how you round, you might get slightly different results. Just make sure you keep it no less than 2 decimal places. and 3 or 4 decimal places is usually best. Okay, so we can say the z-score is 1.645 for 90% confidence. And then it asks what percent is outside the confidence interval. Well, we can see real clearly from this graph that we've got 90% inside. And so that must mean 10% is outside the confidence interval. And then if we extend our thinking further, that must be 5% is on each tail outside the confidence interval, if we're assuming the graph is symmetric. And this makes sense to what we answered in the last part, part B, I think. No, part A, when we were guessing or estimating where the 90% confidence interval would fall. And you can see right here it's between 1 and 2 standard deviations, just like we expected. So down here is a table with the exact z-value scores. And these are calculated from the area. So somebody used either calculus or a computer to make these calculations. I'm not going to make you use calculus or the computer. In fact, you can use your graphing calculator. Question D says use the table values and the formula for the confidence interval to calculate now the 90% confidence interval for psychology majors at LMC. So we'll use the data from example 1, except instead of our standard deviation z-scores we were using before, because this is 90%, we can use 1.645 for our z-score. So our upper bound is going to be 0.17 plus 1.645 times our 0.0208 estimated standard deviation that we calculated before. And then when we total this up, we get 0.204216. For our lower bound, we're going to do the same calculation but with subtraction, still using that same z-score. So this will be 0.17 subtract 1.645 times 0.0208. And that equals out to be 0.135784. So now we can say that we are 90% confident that the population mean is in the interval 0.1358, I'll go ahead and round it, up to 0.2042. So this is our interpretation. We're 90% confident that the population mean lies within this interval. This is just like the calculations we did before. The difference is that now for our z-score we're using 1.645, and this agrees with what we thought before, that the z-score would be between 1 and 2 for 90%. Now we want to calculate for the 99% confidence interval in part E. So we're going to do a similar calculation, except we're going to use the z-score corresponding with 99%. So our upper bound is going to be 0.17 plus 2.576 times 0.0208, and that's going to equal 0.2236. And then our lower bound will be 0.17 subtract the 2.576 times the 0.0208, and that'll be 0.1164. So now we can say that we are 99% confident that the population mean is in the interval 0.1358, comma 0.2042. Oh, I need parentheses around my interval. So make sure you keep yours in interval notation. And so again, this z-score of 2.576 lies between 2 and 3 standard deviations, which is what we expected back in parts A and B. So now if we look up at our chart, you'll notice the 95% z-score is 1.96, and previously we said that it was 2, so you might remember that the 68, 95, 99.7% rule rounds the values slightly. So question F asks, why do you think the z-score for 95% is slightly different from the 2 standard deviations approximation we were using before? So we can say that the 68, 95, 99.7% rule rounds the value of the z-scores slightly. Okay, so the next video will contain example 3.